Hello, AP Physics 1 students. So we just got done talking about the spring force as being a conservative force. So now we can add that to the list. And so right now it brings the list up to 2. We've got 2 forces that are conservative forces. That's the force of gravity and the spring force, which means right now all the other forces we've been talking about are what are called non-conservative forces. So let's talk about that. So I want you to write this statement in your notes and then complete it. So I think it should be pretty obvious, right? If we have our big concept there, our physics pickup line that the work done by or against a conservative force is path independent, then we can clearly say work done by or against a non-conservative force is path dependent. So in this case, the path does matter. The prime example is the friction force. The friction force will change the energy of the system. It will take energy out of the system. So imagine you have a block of wood or something like that, and you're going to scrape it against the floor, right? And so if you go in a straight line, you're going to move it along a certain path in a straight line, and friction will take energy out of the system, which means you have to keep pushing on the block. But then if you start in the same spot and end in the same spot, but you take a roundabout route to get there, the more you're pushing the block against the floor, the longer friction is acting against it, which means that the more you've got to push, because friction is continually taking energy out of the system. And so that's what we mean by path dependent, as opposed to when we deal with conservative forces, it didn't matter how you got from here to there along any path. The work done by that conservative force, the work done against that conservative force is the same no matter what. So what do we mean by this, and how can we interpret this? Well, if we are calculating the work done by a conservative force, in this case WNC, as F delta x cosine theta, well, delta x really isn't displacement anymore. And in fact, it never really was, although we didn't really highlight it as such. Really, in this case, our interpretation is that delta x is more of a path length. And so the longer you are applying that force, longer that force is doing the work, I should say, the more work it's going to do, right? That should make sense. And so think about delta x more like a distance as opposed to a displacement. When non-conservative forces do work, the energy of the system does change. And of course, this is a big difference between this and conservative forces. When only conservative forces do work on the system, then we have conservation of energy. So now we're looking at all the other forces doing work on the system. And that when that happens, the system energy will change. There will be a delta E here, where we are defining WNC as work done by a non-conservative force. So now we basically have 2 categories of forces, non-conservative and conservative. And so we put the work done together by both of those. Well, now we have net work, right? That should make sense. Net work is the work done by all forces, conservative and non-conservative. Now, this equation is kind of interesting because we have expressions for a couple of these terms already, right? So let's rewrite this as WNC plus, and now I want you to fill in the equation we have for the work done by conservative forces. Just look back in your notes. Remember, we generalize the work done by conservative forces as the negative change in the potential energy associated with that conservative force. What about on the right-hand side? We have an equation for W net as well, don't we? Yeah, it's a pretty big one, right? That work energy theorem, that W net is delta KE. Well, let's just play around with this a little bit. So let's take those deltas and split them up, right? So delta PE is, of course, final minus initial, always, always, always. And here I've just put the negative sign on the outside. On the right-hand side, we also have final minus initial. And now I want you to distribute the negative sign and play with the algebra a little bit. You can leave WNC on the left-hand side, but then move all the initial stuff over to the left and all the final stuff over to the right. Pause the video, go ahead and do that. Okay, so distributing the negative sign, of course, just means switching the signs on those, and now move all the initial stuff over to the left, all the final stuff over to the right, and here we have an equation we can box in. You see, this is quite similar to conservation of energy, but now it allows for all situations. What if we don't have conservation of energy? What if we do have work done by some non-conservative forces? So that's why I'm boxing in this version as opposed to the one from before, because this allows for all possibilities. Let's in fact look at some of the possibilities here. What could happen with the non-conservative work? So let's say, for example, if WNC is greater than 0. So pause the video and write down what you think that means. Right, just think about this. It means that the system starts with some kinetic energy and potential energy, or some total energy, and then WNC adds in extra, which means that the final energy is going to be more than the initial, which means the system gains energy. This happens all the time. An object is at rest, and if you want it to move, you with your non-conservative force are going to do some non-conservative work and add energy into the system. Otherwise, if you don't, guess what? The object doesn't move, right? And so this happens all the time. You certainly can add energy into the system by doing some non-conservative work. All right, so what if, in this case, WNC is less than 0? Pause the video, write down what that should be. Yeah, I hope you got that the system loses energy, right? So again, on the left-hand side, we have some starting energy, kinetic potential, a mixture, whatever. And then if WNC is negative, well, then the right-hand side will certainly be smaller than whatever it is you started with. So that means the system loses energy. The prime example here, of course, is friction. Work done by friction almost always takes mechanical energy out of the system. Of course, we do have a third situation. What if WNC equals 0? So pause the video, write down what you think that is. And of course, now we have conservation of energy, right? So if you just take WNC as equal to 0, we're right back to our law of conservation of energy. No non-conservative work being done, only work done by conservative forces. The total energy stays the same. And that's really the definition of conservation of energy.